Riemann sums are all fine and good, but let's talk about something a little bit spicier. It's called Simpsons Rule. In general, Simpsons Rule will actually give us a better approximation than any Riemann sum. I might be generalizing there, I'm not sure. Probably there's some pedantic way of being like, oh, that's not true, but I'm going to stick with it. Simpsons Rule gives us even better approximations than our Riemann sums. Simpsons Rule says that this integral, a to b of f of x dx, can be approximated as delta x over 3, delta x being the width of each subinterval, times f of a plus 4 f of a plus b over 2 plus f of b. This middle term, a plus b over 2, that's halfway between a and b. It's the average of a and b, so it's not as complicated as it seems. And this rule, by the way, is for two equally spaced subintervals. We'll talk about what to do when there's more subintervals. But for now, two equally spaced subdivisions. So if I were doing integral from 2 to 10 of f of x dx, I would approximate this as, okay, Simpsons Rule says I do delta x over 3 f of a plus 4 f of halfway between a and b plus f of b, which in this case, if I'm going from 2 to 10, that's a width of 8. And if I'm breaking that into two subintervals, each subinterval must have a width of 4. My delta x is going to be 4. So I'm going to do 4/3 f of 2 plus, and it's going to end with an f of 10. In between goes 4 f of the middle number. Between 2 and 10, I hit 6. So this is going to be 4/3 f of 2 plus 4 times f of 6 plus f of 10. If I do 17 minus 8 plus 7, it makes 16 times 4/3. So 64/3 would be my answer for this one. We'll do another. If I were approximating integral from 1 to 17 of square root of x, Simpsons Rule says I do delta x over 3. If I'm going from 1 to 17, that's a width of 16. If I'm doing it in two pieces, each piece must be 8. My delta x must be 8. So I'm going to do 8/3 times f of 1. I'm going to have an f of 17 in there. And in between we'll go 4 times f of whatever's halfway between 1 and 17, which is 9. So 8/3 f of 1, square root of 1, 4 square root of 9, 4 times square root of 9, square root of 17. I've got 8/3 times 13 plus root 17. So I guess that makes 104 plus 8 root 17 over 3. Okay, but so what if it isn't two subintervals? What if I want to do more subdivisions? With Riemann sums, more subdivisions means better approximation. Simpsons Rule, maybe I want to use more. If I want to use more, I just do Simpsons Rule on two subdivisions at a time. What I mean by that is, say I'm going from 1 to 17, and I want to do it with 8 equally spaced subdivisions. If I'm taking a width of 16 from 1 to 17 is 16 units, I'm doing it in 8 steps. Each one must be 2. So I'm going to go 1 to 3 to 5 to 7 to 9 to 11 to 13 to 15. I didn't draw that quite to scale. And I do Simpsons Rule one piece at a time. First I do Simpsons Rule on this piece. Then I do Simpsons Rule on this piece. I do that kind of two at a time. Then I do this piece. Then I do this piece. So Simpsons Rule to approximate just the first piece from 1 to 5 would be delta x over 3 f of 1 plus 4 f of 3 plus f of 5. And then that next piece would be delta x over 3 f of 5 plus 4 f of 7 plus f of 9. And then I'd have a piece that goes 2/3 f of 9 plus 4 f of 11 plus 1 f of 13. And my last piece would be delta x over 3 f of a 4 f of halfway between a and b f of b. And I would add this all up. What makes sense is if I actually add it up by thinking about combining like terms first. If I add all these up, it's 2/3 times it all. And I'm going to have 2/3 times an f of 1. I have 4 f of 3's in there. And then I have 2 f of 5's. I have an f of 5 here and an f of 5 here. So plus 2 f of 5. I already have these in there. Now I need 4 f of 7's. When I do Simpson's approximation on something with more than just 2 equally spaced subintervals, it always works out like this. I always get this pattern where I do f of every little number, every little endpoint of a subinterval, and the pattern goes 1, 4, 2, 4, 2, 4, 2, 4, 1. It always starts with a 1, ends with a 1, and in between goes 4, 2, 4, 2, 4, and it's 4 on the ends. If that makes sense to you, it makes sense to you. If not, whatever. I add all those up, and it comes out to, I paused because I thought I had it done on a piece of paper already, but I have on my paper is 2/3, 1 plus 4 root 3 plus 2 root 5 plus 4 root 7 plus 2 root 9 plus 4 root 11 plus 2 root 13 plus 4 root 15 plus root 17. And the 1 and the 6 can combine to a 7, whatever. Let's do 2 more. This one's interesting. I'm going to surprise you with how this is interesting. This time, only 2 equally spaced subdivisions. Wonderful! This is going to be approximately, if I'm going from 0 to 4 in 2 subdivisions, each subdivision must have a width of 2. So I do delta x is 2 over 3 f of 0 plus 4 f of 2 plus f of 4. I do f of a here, f of b here, and f of halfway between a and b here. So this comes out to 2/3 f of 0. By f, I mean this thing here. So f of 0 would be 1 plus 4 times f of 2 is 5. F of 4 is 17. You get 2/3 times 1 plus 20 plus 17, so 38. This comes out to 76 over 3. Is approximately what this comes out to. And if I were to actually do it, I would get 76 over 3 is the actual answer. Oh my goodness, they're the same number! It's fantastic! And the crowd goes wild. The crowd goes wild until I tell them that the trick. Simpsons rule always gets quadratics exactly correct. If I integrate a quadratic, Simpsons rule gets it exactly correct. And that's because Simpsons rule is actually based on approximating a function by pretending it's a quadratic. Say we're approximating between A and B. This looks like a cubic that I drew. Simpson's rule would look at this point, would look at halfway in between, and look at this point. Think about it as a quadratic, and would just find the area under the quadratic. So if it already has a quadratic, it gets it exactly right. If that made sense, wonderful. If not, just know Simpson's rule doesn't just approximate, it gives you an exact answer when integrating a quadratic, and you only need to do 2 subdivisions, so it makes finding a definite integral of a quadratic very easy. Last one, Simpson's rule, 6 equally spaced subdivisions, this. Let's see, if I have from 2 to 20, that's a width of 18. If I'm breaking it up into 6 subdivisions, each one must be a width of 3. So when I do my delta x over 3, I'm going to do 3 over 3. And I know my rule is I'm going to be doing f of all the little things in between. Here I have 2, 5, 8, 11, 14, 17. That's 1, 2, 3, 4, 5, 6 subdivisions. I'm going to do f of all those things. But I remember from that slide from before, let's see, f of 17, I remember that there's a rule for what goes in front of these. Right, the long way would be to do this by just doing from 2 to 8, then 8 to 14, then 14 to 20. But I remembered I could just do this thing where I throw on the coefficients 1 and 1, and then in between it goes 4, 2, 4, 2, 4, like that. So this is going to be 3/3 is 1. F of 2 plus 4, f of 5 plus 2, f of 8 plus 4, f of 11 plus 2, f of 14 plus 4, f of 17 plus f of 20. That comes out to 2.342. Just for the fun of it, I actually figured out the exact answer for this. If I were to actually do the integral, it comes out to ln of 10, which is 2.303. So Simpson's rule came pretty close.